I know that's a little hard to read, but basically it says that, hey, this airplane experiences an air resistance proportional to the square of its speed v. And there's an additional air drag induced by lift, and it's present, and it's inversely proportional to v squared. So the total air resistance can be described as alpha v squared plus beta over v squared, where alpha is 0.3 newton second squared over meter squared, and beta is 3.5 times 10 to the fifth newton times meter squared over second squared. So we have two constants here, and there is some air resistance, right? So there's just your traditional air resistance that's like proportional to the square of the speed, but there's also this induced air drag where the air, it's caused by like the flow of the air. Some of the air gets pushed forward. So by Newton's third law, there's going to be some more drag that's inversely proportional to v squared. So we could say that the force by the air the force air resistance is equal to alpha v squared plus beta v squared. Okay, so in the steady flight, the engine provides a forward force to exactly balance out the air drag, right? So for a given quantity of fuel, at what speed will give, that was wrong. What speed will give the airplane maximum range, travel the greatest distance, and maximum endurance, remain in the air for the longest time. So if you have a certain amount of fuel, how fast would you have to be moving to get the most range and the most time in the air? So pause this video, try it out on your own. I hope you paused and at least tried and at least kind of appreciated how cool of a problem this is. Let's just get into it. It's an energy problem, right? We got to think about energy, because if we have a given quantity of fuel, right? Let's just write down the energy equation. We're gonna have some kinetic energy, right? Oh, this marker's dead. All right, don't use this one, I guess. If we have some kinetic energy to begin with, right? We're gonna have the same kinetic energy afterwards, right? Because we're moving at a constant speed. The force, so if we have the FBD, right, the force by engine balances out the total air drag, right? So kinetic energy will remain the same, but there's going to be work done by the engine, right? And there's also going to be work, done by the air resistance that removes energy. There's going to be negative work done, by air resistance. So we can just label it like that. And the engine's kind of, you can say it's internal to the system. So this work done by force engine is like kind of it's changing fuel, chemical energy, whatever. We could just call it as work done by the engine. And hey, these kinetic energies are the same, so we get that the work done by the force engine has to equal the work done by the force of air drag, right? Whatever energy the engine adds to the plane, the air resistance is going to take it away in order to move at the same speed. So this work that represents how much energy it has, right? How much fuel is in the tank, right? Because if it can do very little work, that means there's very little fuel in the tank, right? So and once that engine runs out, you kind of can't do anything from there. So this is going to kind of stay constant. This is what the given quantity of fuel means. Hey, you have this much work you can do. What speed can you kind of maximize the range? How far you're going to travel? Because if you think about it, if you move super duper fast, you're going to have a really high air resistance. So you're going to be moving. You're going to have to you're going to have to like sort of output a lot of you're going to have to what's the word? Like you're going to have to really high force. And if you're also moving really slow, we have that inverse proportionality as well. So if you're moving really slow, you're also going to need air, like a really high amount of force. So let's actually just substitute in some things here. We know that the engine is going to output. Oh, this marker also did? Okay, so cat markers. That's a new thing we learned. We know that there's going to be a forward force by the engine, and that forward force has to balance out the air resistance. So if we write force times distance, this is just our work formula, and then we'll say theta, right? Because everything is parallel. It's we don't have to worry about angles. So the air resistance is gonna, just plug in that equation they kind of gave us over d. So the distance can kind of cancel out, right? Because for every, it's this, you go 3 meters, this force adds that much energy, and if you go 3 meters, it removes the same amount of energy. The distance is kind of like the same, right? We don't really know how far it's going to travel, but it's also not really important, because we're not finding the range, we're just finding the speed, which is in this equation. So we know that, hey, the force has to equal alpha v squared plus beta over v squared. Well, I said distance kind of cancels out, but what I want to show you is that even though the distance will kind of cancel out here, and this is also just, actually I didn't really need this actually, this just comes from this force has to balance the air resistance, but also if we have this constant amount of energy, we said this was constant, in order to get the highest distance possible, you need to output a very low force, right? We need the lowest possible force. So really what we're trying to do is, if this is a function, like the whatever the velocity is, or speed, this is what the force you need to kind of balance that out. We got to find the minimum. So we got to find, well, what's the minimum force? What's the minimum, what speed will get me the minimum force, right? Because if you graph this, you can imagine it's going to, going to kind of curve like this, right? Because, when you get really high speeds, then you're going to get really high, v values, and when you get really low speeds, you're going to get really high values as well. There's going to be some point kind of where the minimum, right? So let's actually try to figure that out. Let's figure out, well, when is the force at a minimum? Well, in order to do that, you gotta find, actually just not erase that, you gotta find what's that extrema, what's that like point, that critical point where the slope is 0, and that's where our minimum is gonna be. We can just do the derivative, right? So if we differentiate this function, we would get that, okay, let's do power rule, right? We have 2 alpha v plus, and then we're going to do a minus here, and then we're going to get, okay, 2 beta over v to the third. And if you're kind of confused where that all came from, I just took the derivative of this function, and you can watch a lot of great videos, I don't know, on Khan Academy or something, of derivatives. And then we just gotta find, well, when is this equal to 0, right? I'm not saying that force is equal to 0. I'm just saying that in order to find that minimum value, we're just finding when is a derivative equal to 0. Then it's just kind of solved, right? 2 beta over v cubed is going to equal 2 alpha v. So we can multiply everything by v cubed. We can get 2 beta over 2 alpha, with the 2's cancel out, is going to equal v to the 4th. So then, really, we have beta over alpha, 1/4 power, taking the 4th root, is going to equal v, and then that is just what we got to do. We just got to plug in the beta and alpha that they gave us. So the key idea here was you have to understand, hey, you're outputting that same energy, or you have a certain amount of energy. In order to minimize force, in order to maximize distance, you have to minimize force, and you can do some calculus to figure out, well, what is the lowest possible force you can get while still getting the same amount of distance. All right, so now that I did that, we can try out the second part of this thing. I'm just going to see how much time I have. 8 minutes. Okay, I'll make this next part quick, because one way you can kind of think about this next part is we're trying to maximize time. Well, what's an equation that kind of has time and energy? Well, that's the power equation, right? Power is equal to, I almost said a bad word there because these dead markers are kind of annoying me. Power is equal to work over time. So if you want to maximize your time for a constant amount of power, constant amount of energy, you're going to need a really low amount of power. Now, what's another equation for power? Power is the same thing as, it's the same thing as, what's it called? Force times velocity, right? Because you can change this to force times distance over t, and you get force times velocity is equal to power. We're trying to get the lowest possible power. So, the power by the engine has to equal the power by the air drag, right? Because they're both doing the same amount of energy, right? And if they're in the air for the same time, right, it's going to be the same power. So low power by air resistance is what we kind of need here. So what we can do is say, okay, same idea. We're trying to find when is this low. Let's just actually plug in the force equation for air resistance, which is right here. Oh, I didn't even give you the answer for the last one. I'm so sorry. I was gonna do that. If you plug in everything, if you do the beta over alpha to the 1/4, you should get, well, I did this in kilometers per hour because that's what the question asked in the textbook. I think it was like, I don't remember. I don't actually remember. Just take whatever you got in meters per second, multiply it, divide it by 1,000, and then multiply by 3,600. You should get this. So same thing here. We're just gonna do 3 alpha v. Why am I doing 3? Sorry, alpha v squared, but we're also multiplying by v, so we're gonna do cubed plus. Is this also dying? Oh no. My markers. Then we're also going to get the beta v squared times v is just beta over v. Is an equal power. We're trying to find the lowest power. We're trying to find, this is right. We're trying to find the lowest power. We're trying to find when is, for this graph, when is it at its lowest value. We got to find when is the derivative equal to 0. Same idea. We're going to do the derivative is 3 alpha v cubed. That's why I was putting in v. Minus beta over v squared, and this just comes from power rule, right? I'm just doing some power rule stuff here, and yeah, then you're just finding, hey, when is it equal to 0? Then you could solve 3 alpha v squared is going to equal beta over v squared. We have 3 alpha v to the 4th is going to equal beta v to the 4th is equal to beta over 3 alpha, or v is going to equal to the 4th root, of 3 beta over 3 alpha. And you have alpha and beta, they're given to you, you plug that in, and you should get, in kilometers per hour, so whatever number you got, divided by 1,000, multiplied by 3,600. If you're actually doing this problem, I owe you $1 million, but you should get 89.9 kilometers per hour. So that is kind of the speed you got to travel at in order to maximize your endurance, right? Because if you move super fast, you're going to run out of fuel real quick, but if you also move really slow, you're going to also run out of fuel real quick. So you just got to make sure your power is the lowest, right? Like you're playing a game where power runs out and you're in a, office and you got to protect yourself from animatronics. All right, so thank you for watching this quick energy video. I just thought it was a cool problem, so thought I'd share on my YouTube channel.